Alright, good morning, good afternoon, good evening class. This is Mr. Arocena, and on today's video, or today's lesson, we're going to be talking about calculations involving Ka. Now, in previous lessons, we've talked a lot about what this actually means, like what is Ka and what is Kb and Kw and so on. Now, before we actually dive right into the examples, we'll revisit equilibrium tables. If you remember our equilibrium tables, we called them Rice tables. And it stood for the following, where you, at the beginning, the top of the table, you wrote down your reaction. And then you followed up with initial concentrations. Remember, it's concentrations, not moles. The next row was change in concentration. And finally, you had equilibrium concentrations. We're going to be using these tables again as we talk about Ka calculations and by extension Kb calculations, because if you recall our talk about weak acids and weak bases and other things that had Ka values, they were really just equilibrium constants. But now, why do these equilibrium constants exist? Well, this will go back to our definition of what a weak acid and weak base do compared to a strong acid and strong base. A weak acid, we'll just call it HA for now, generic weak acid, when it dissolves, only some of the acid will actually ionize. So I have a picture here of what will result when the solution dissolves. When you dissolve a weak acid into a solution, you will contain some of the non-ionized acid, so it's the undissolved acid. So this one here is undissolved acid. It will contain some of the dissolved acid, which by I guess by extension this is the conjugate base. And finally, the result, or the thing that makes an acid is hydronium. So a weak acid contains all three of these. Because not all of the acid dissolves, there will be some amount of undissolved acid left. There will be some amount of conjugate base, and there will be some amount of hydronium. All three will exist. By contrast, a strong acid, strong acids fully dissociate, fully dissolve. So no equilibrium is established. And this is something you have to keep in mind. Okay. So everything we kind of deal with from here on out, at least in this section of the unit, are going to be weak acids. Okay, we'll revisit strong acids again at a later point, but for now, we're going to talk about weak acids. Now, Ka calculations fall into kind of three types of problems. The first of which is, I think, the most straightforward one, is that if you're given the concentration of the weak acid, they're asked to find the Ka. Or sorry, if you're given the concentration of the weak acid and you have its Ka, you can then find the concentration of H3O+, and by extension, pH. Because if you remember, pH is based on the concentration of H3O+. The second type is if you're given the concentration of the weak acid and you have the pH, or the concentration of hydronium, then you're asked to find the Ka. And the last one is if you have the concentration of hydronium, or the pH, and the Ka, then you're asked to find the concentration of the acid. The next lesson, calculations involving Kb, are pretty much the same. We just replace all instances of acid with a weak base and all instances of hydronium with hydroxide. But we'll get to that in a future video. So these are the three types of examples we're going to go through, and they're a little lengthy because if you remember from our equilibrium calculation unit, so yeah. Some of these calculations can get quite involving, but they're not overly difficult if you set your Rice table up correctly. Alright, so this first one comes straight from the textbook. It's on page 149, and we'll go through it. It asks, what is the pH of a 0.5 molar solution of CH3COOH? This is not a strong acid, so you can't immediately just do negative log of this, because not all of that is acetic acid. Not all of this acid is going to dissolve to create an equivalent amount of hydronium. So we'll approach this problem as follows. What values are given, and from there we can decide which type of problem it's going to fall into. So here we are given the concentration of my weak acid, 0.5 molar. We're given the name of the weak acid, so we can find its Ka. Let's just do that real quick. Okay, so here's the table. We're looking for CH3COOH. There it is, acetic acid. It has a Ka of 1.8 times 10 to the negative 5. 1.8 times 10. Alright, now where do we go from here? We're going to need a little bit more room. Alright, so we've got a little more room. Let's work this out. So we're going to use a rice table to work on this. So let me just write it out. Now the reaction, it's not explicitly stated, but this is just a generic acid reaction. So we can say the following. Our acid plus the water will produce hydronium and a conjugate base. CH3. All right, initial conditions. Let me just finish out the table so everything is nicely separated. This column we don't care about because water doesn't actually affect the equilibrium calculations being a liquid. So let's see. The initial conditions, we have 0.5 molar. Initial condition H3O plus is 0 and conjugate base is 0. Now the change, when this dissolves, it makes sense that the equilibrium will shift forward initially because we have none of that. So this will gain X, this will gain X. So this becomes 0.5 molar minus X, and these just become X and X. Now, given the definition of what an equilibrium constant is, Ka is going to look like this. Concentration of products. So the CH3COO minus divided by the concentration of the reactant. There we go. So no different than any other equilibrium thing we've done. We're just applying it specifically to acid-base reactions now. Placing the values we know that the Ka is 1.8 times 10 to the negative 5. Concentration of H3O plus is X. Concentration of this CH3COO minus is X. The concentration of this acetic acid, is going to be 0.5 minus X. Okay. And what we're going to do now, and this is going to for those of you really mathy folks, this is going to make you kind of cringe a little bit. For everyone else, it's going to be a very important tool we use. We're going to say the following: 0.5 minus X is going to be, we're going to make this assumption. And the reason we're going to make that assumption is because X is going to be much smaller than 0.5. Okay. So we're going to make this assumption. This is to make the math easier. And when we finally figure out what X is, it'll actually make a lot of sense. I'm actually not sure if we did this assumption in the equilibrium unit. I want to say we did, but I'm not certain. Anyways, we'll make the assumption now. Alright, so now it makes it a lot easier. So, carrying out the calculation, I see 0.5 times this, that'll get me 0.9 times 10 to the negative 5 squared. Square root everything. So now we get the following: X is equal to, calculator gives the answer of 0.003. That will be in molarity. Now, going back to our assumption, we can make that assumption. The assumption still holds just fine because 0.003 is actually quite a bit smaller than 0.5. So our assumption is justified. Now when you do the calculation, you get the following. So 0.5 minus 0.003 will get me 0.497 molar, and these will be 0.003 molar and 0.003 molar. Now the question I think was asking us for the pH, right? Yes, pH. We know the concentration of H3O plus is here. So now we can just use our pH calculation. So pH is negative log of the H3O plus. So this will be negative log 0.003, and that will get us 2.5. There you go. So the pH of 0.5 molar acetic acid is going to be about 2.5. Which is about right. Vinegar usually has a pH of around between 2 and 3, depending on the concentration of it. Next example then. Oh, but wait, I forgot. Note. Now, our initial assumption, or the assumption that the 0.5, so our assumption is justified. So again, this is referring to the fact that when we, in our equilibrium table at 0.5 minus x is approximately 0.5. This is justified because the change in concentration is really small compared to the original concentration. Like I think our concentration change was 0.03. So really the change in concentration doesn't really change. Oh wait, 0.03. So change is even smaller. Now, if you do this calculation and the change ends up being actually rather significant, and by significant, our sort of baseline for that is going to be 5%. So if this change was on the order of say like 0.15 as opposed to 0.003, that's significantly larger and actually has an effect. Okay, so as long as your change is about 5% or smaller than the original amount, then we can make that assumption. We can make this assumption that the equilibrium concentration of the original acid is going to be about the same as the original equilibrium concentration of the acid. It really doesn't change all that much. On to the second example. In the second example, we are asking for not the pH this time because we were given the pH. The pH is 0.1 molar. We don't know what the acid is, and then we're asked to find what the Ka is. So similar to example 1, we'll start off as follows. What values are given? In this case, we are given the pH. Oh wait, pH has no units. And then we are asked to find what the Ka is. Okay. Now from here, it looks like we're given even less information because we don't even know what the acid is. But there's a couple of things we can work with. Let's get some more room. All right, so we're going to start with our rice table. And even though we don't have a lot of the information, there's still some parts we can fill out. Okay, so we have a generic weak acid. We don't know what it is, so it's called HA. It's reacting with water, and it's going to produce some amount of hydronium and some amount of unknown acid. Now, as you're filling this table in, you might actually notice something that's really interesting. Obviously, the H2O doesn't matter in our calculations because it's water. It's a liquid. Liquids don't affect equilibrium if it's the only one. We don't know what my concentration of my acid is, so I'll call it... Oh wait, no, we do know what the concentration of the acid is. It tells us right here, 0.1. Oh. This starts off at 0. We know that this is going to change. We know this is to change. Oh wait, this is going to be a plus, and this is going to change like that. This will be x, this will be x, this will be 0.1 minus x. And again, we're going to make the assumption, assume 0.1 minus x is approximately 0.1 for the purposes of doing the Ka calculation. All right, so we fill it in our table with the information we are given. We know that to calculate Ka, it's going to be the concentration of the product. So in this case, our hydronium concentration times our conjugate base concentration divided by the concentration of the weak acid. We don't know Ka because we're asked to find. We do know what this is, but we don't know what either of these are. However, we are given the pH. And if you recall from an earlier lesson, when we were talking about pHs, you can calculate the concentration of hydronium as 10 to the negative pH. So here we have the concentration of hydronium now, because we know what the pH is, so we can go 10 to the negative 1.7, 0.02 for argument's sake. Yeah, about 0.02. So 0.02. So now we know the concentration of hydronium. So here we can say, okay, if that's the concentration of hydronium, this will be 0.02. And then by extension, because the concentration of hydronium and the concentration of the weak base are the same, then we can say 0.02 molar as well there. Now we have all the information to calculate Ka. Now the concentration of hydronium, 0.02 molar, concentration of conjugate base, 0.02, concentration of the original acid, which is 0.1, and now we can calculate Ka. So in our calculator, 0.02 times 0.02 divided by 0.1, we have a Ka of 1 times 10 to the negative 1. Yes, I thought I missed it. There we go. So even though it looked like we didn't have enough information to calculate it, at the end of the day, we did actually have enough information to calculate it. Just be mindful that if you're given the pH, you can calculate the concentration of H3O+. All right, on to the third example. So example 3. Here we are asked to find what mass of NH4Cl will produce a 1.5 liter solution with a pH of 4.75. Now, again, it looks like there's a lot of information that we're missing. So we'll start off by asking what values are given. We have a pH 4.75. Have a volume 1.5 liters. The volume will come into play later. We don't actually need the volume right away, but it'll come into later. And we're given a substance NH4Cl. Now at first glance, this substance doesn't actually look like an acid or a base, but if you recall from the last video, some substances, some ionic substances, when they dissolve in water, now thankfully this is a ammonium based substance, so we know that this will fully dissolve to its respective ions. Some of these ions can actually react with water to either act as an acid or as a base. In this case, if you recall from the previous lesson, this will react with water. Following NH plus will react with water to create hydronium and ammonia. Now we can find the Ka, because hey, this substance here can act as an acid, probably shows up in our table. There it is. NH4 has a Ka of 5.6 times 10 to the negative 10. 5.6 times 10 to the negative 10. And then the question is asking us to find the mass. We're going to need a bit more room. All right, I've already started the rice table by writing down the reaction, so I might as well just continue on with here. Save myself a bit of time. Now, some of you, while I'm doing this, might have realized that these are actually quite a bit simpler than the previous equilibrium calculations we were doing, because currently everything seems to be a 1-to-1-to-1 ratio, which is amazing. It's actually quite helpful for us that way. Alright, let's see. We do not know anything about the initial concentration. Know that this starts off at 0. This will require us to use two variables, unfortunately. So the change we'll call y. We're going to make that same assumption we did before. Assume x minus y is approximately equal to x, so that it'll make our math easier. This will be plus y, this will be plus y, and these will be y. Now some of you might be wondering, well, that doesn't really change our equilibrium expression, because our equilibrium expression will still have multiple variables. Now while I'm writing this out, you might think about that statement and ask yourself, does it really change? Or sorry, do we really have two unknown variables? I mean, initially, yes, it does look like we have two unknown variables. But if you think about it, we can probably calculate, actually we can calculate one of the unknown variables. There we go. And by now, hopefully you guys have realized that yes, we actually can calculate one of the unknown variables, because much like the previous example, we are given the pH. So if we are given the pH, we can then calculate the concentration of H3O plus as 10 to the negative pH. Which in our case is 10 to the negative 4.75, which will be 4.75 to the 10 to the 4.75, so 1.78 times 10 to the negative 5. 78 times 10 to the negative 5. So that's this number here. So this number is 1.78 times 10 to the negative 5. It's a ridiculously small number, so our assumption is probably a-okay. Now, because the concentration of hydronium will match the concentration of the conjugate base, we can say the same thing here. Alright, now, even though our original equation showed two variables, one of the variables we were actually able to calculate for, and now we can finish off our calculation. Ka is 5.6 times 10 to the negative 10. Alright, let's do a little bit of algebra. So x will be 1.78 times 10 to the negative 5. This will be squared by 5.6 times 10 to the negative 10. Putting this into our calculators, we will get the following. Okay, 1.78 times 1.78 divided by 5.6, 0.566, 0.566 times 10. 10 to the negative 5 squared is 10. Divide this by 10 to the negative 10. So it looks like x will be 0.566 times 10 to the 0. Or 0.56, and that'll be in molar. Right, so now this x is actually the concentration of the NH4+. There we go. All right, are we done? No, because the question was asking us what mass of, now I've got to figure out what's the mass of NH4Cl. That's what the question was asking us. So finding the concentration of NH4+ is really kind of just a stepping stone. How do I get the concentration, or how do I get the mass of NH4? Well, if you remember, the problem gave us the volume of 1.5 liters. Well, if that's the concentration of NH4+, I can use our molarity equation to find out our moles of NH4+. Moles of NH4+ we can calculate using volume times molarity. So let's calculate how many moles of NH4+ we have. Why am I calculating moles of NH4+? Well, eventually we're going to need to use the mole to mass relationship to find out the mass of NH4Cl. And currently we only have information to calculate moles of NH4+. So that's why I'm doing this. The 1.5 liters times the concentration of 0.566 molar equals times 1.5, about 0.85 moles, 849 moles. We'll go for now 0.849 moles. But wait, we want the mass of NH4Cl, not mass of NH4+. Well, we're gonna go back to the first equation I wrote, first chemical equation I wrote, which was the dissolving of NH4Cl to this. Okay, so if I have this many moles of NH4+, using our balanced equation, which it is balanced, how many moles of NH4Cl are going to be necessary? Well, we have a 1-to-1 ratio, so we have 0.849 moles of NH4Cl as of our balanced equation, showing the relationship between the moles of NH4+ and the moles of NH4Cl. Are we done? No, not quite, because now we have the moles of NH4Cl, we need to calculate the mass of NH4Cl. And to go to mass, we simply multiply by the molar mass of NH4Cl, which I'm actually not sure of, but I can do the calculation quickly. So nitrogen is 14, 4 hydrogens is 4, and a single chlorine, I believe, is 35.5. Let me check. Yes, chlorine has a molar mass of 35.5. Altogether, that is 14 plus 4 is 18, 18 plus is 53. So take our moles, 0.849 times the molar mass of 53.5, get a mass of 45.4 grams. And I think we only need two significant figures, so 45 grams NH4. There we go. So this problem kind of took all the stuff we learned from our equilibrium unit and combined them with some mole math and to get the final answer we need for this question. So, like I said, the problems are kind of involving, but take it slowly, step by step. Don't forget to don't skip steps, and the problems are not overly difficult. And remember that even though it may seem like you don't have enough information, fill out the table as best as you can and then look over what you've done. Now, to make our lives a little easier, there's another thing we can consider. Okay. And this is especially useful for polyprotic acids. And that's the fact that we only need to consider the first hydrogen donation in a polyprotic acid. So consider here, this is oxalic acid. It's a polyprotic acid, has the ability to give two hydrogens. But when doing Ka calculations, we only need to consider the first hydrogen donation. And the reason for that is that the second hydrogen donation, so this one donating hydrogen, so donates a very small amount that can be safely ignored. And this is true for all polyprotic acids. We only need to consider the first hydrogen donation. Okay, so if we had phosphoric acid, this has the ability to donate like 3 hydrogens, but we only need to consider the first one because the H2PO4, the amount that this donates, so this can donate to become HPO4 minus, or HPO4 minus. This reaction occurs way less. Yeah, way less is probably the best way to put it. Occurs way less than the first reaction. And one way you can sort of think about it is that the first reaction will create a whole bunch of hydroniums. So this equilibrium, sorry, these are equilibriums. this equilibrium here, the H2PO4 equilibrium, is less likely to create hydroniums because there's already a bunch of hydroniums present. So the second equilibrium is less likely to create hydroniums because the first equilibrium has already created them. And if you think back to Le Chatelier's principle, that's kind of what it wants to do. It doesn't want to create more, it'll probably want to create less. So that's why this second equilibrium doesn't happen as often. And it actually makes our Ka calculations even easier because now we can basically consider everything is going to end up being a 1-to-1 ratio. It's going to be much simpler than what we were doing previously in our other equilibrium calculations. All right, with that said, those are 3 examples. 3 types of problems. You should be able to complete this assignment in your textbook. If you have any questions, you guys all know how to contact me.